So far, we've discussed two methods for solving systems of linear equations, by graphing and by substitution. Graphing is great because it lets us visualize the relationship between the equations in the system and lets us know whether the lines are parallel, coincident, or if they intersect. The hard thing about graphing is if the point of intersection is a fraction or a decimal, then it can be very difficult to ascertain its value. Substitution was our first algebraic method, and substitution is great when one of the variables in the system has a coefficient of 1 or -1, because this makes isolating the variable very simple. Our second algebraic method is called elimination, and this is good to use when none of the variables are easy to isolate without causing, fractions or decimals to arise in the equations. In this method, we'll focus on multiplying one or both of the equations by a constant to scale the equations so they have certain characteristics. So let's go ahead and look at this first example, and I'll explain what these characteristics need to be. So here we have a system. Our first equation is 2x plus 7y equals -1, and our second equation is 5x minus 7y equals 22. Well, something you may notice right away is that our y values have coefficients of +7 and -7. So remember, when solving a system, you need to combine the equations in some way. When we were graphing, we combined the equations by graphing them on the same coordinate plane. In substitution, we combine the equations by solving for one variable and then plugging in its equivalent expression into the other equation. All right, so in elimination, we're going to focus on adding the two equations. But in order to add the two equations and make any headway or make progress, one of the variables, so either x or y, has to have coefficients that are equal in number but opposite in sign. So we see that the coefficient of the y is +7 and -7. So if we were to add these two equations, we would see that 2x plus 5x equals 7x. We would also see that +7y and -7y cancel. So there are no more y's. And -1 plus 22 is 21. So by adding these two equations, I eliminated the y variable, and I can easily solve for x by dividing both sides by 7. So we see that x equals 3. Well, all right. As before, once we know the value of one of the variables, we're just going to go ahead and plug it back in and solve for the other one. So let's plug it back into the first equation. So 2x, so 2 times 3, plus 7y equals -1. So 6 plus 7y equals -1. 7y equals -7. And once again, we'll divide both sides by 7. And y equals -1. Well, okay, there's my ordered pair. My x value is 3, my y value is -1. So the point of intersection of these two lines is going to be the ordered pair 3, -1. And of course, we can always go ahead and plug them back in to both equations just to ensure that they work out, and I would challenge you to do that. So here's our first example, and it was set up pretty nicely for us because the y's automatically canceled when I added the two equations together, and it did not require us to scale either of these equations or multiply them by anything. In this second example, we're going to use elimination once again to solve this system, and you'll notice these aren't written in any particular form, so what we need to do first for each of these equations is change it to standard form. So it's going to be xy equals number, xy equals number. So we need to have the x's and y variables over on the left side together and the constant on the right side. Everything needs to be lined up appropriately. So in order to facilitate this in the first example, we're going to move this +3y over the left and make him -3y. And that will equal -12. In the second equation, we'll facilitate that by taking the -2x and moving him over to the right and making him +2x. This 5y is positive, so I'll put a plus right there. And now we see that x, y equals number. We kind of have it set up in the right format. All right, well, let's focus next on the coefficients of these variables and decide whether it would be better to eliminate the x's or the y's. So a lot of this process is going to be like number sense skills, considering greatest common factors, least common multiples, and things of that nature. So let's go ahead and start with the x's. So we'll look at 4 and 2. Can I multiply 4 by an integer to get 2? Well, no. Can I multiply an integer by 2 to get 4? Well, yes, because I can multiply 2 by 2 to get 4. Okay, so x's seem like a pretty good candidate. Maybe let's look at the y's real quick. Is there an integer I can multiply by -3 to make 5? Well, no. How about the other way around? 5 to get 3? Well, no again. So the x's are going to be a great candidate here. So recall, in order to add these two equations together and get one of the variables to cancel or eliminate, their coefficients have to be equal in number but opposite in sign. So this is a +4 and a +2. So let's go ahead and multiply the second equation by -2, because that would cause my x's to be -4, and that would go nicely with the +4. But remember, when we're scaling this equation or multiplying by -2, we need to multiply every single term in the equation by -2. Probably the most common mistakes is students forget to multiply the constant over here. So let's go ahead and do that. So -4x minus 10y equals -40. And let's just go ahead and rewrite the first equation. It's left unchanged, so I'm just going to copy it down here. And when I add these two equations together, we notice that the x's cancel. -4x, +4x. So that's by design, of course. Our y's add up to give us -13y, and our constants add up to give us -52. So I can do a quick division by -13, and I'll see my y value will be 4. Well, fantastic. So let's go ahead and plug that back in now and solve for x. So again, it doesn't really matter where we plug it back in. Maybe because x is almost by itself here, let's go ahead and plug the value of y into this first equation. So 4x equals 3 times y, and y was 4. So 4x equals 12 minus 12. 4x equals 0. So when I divide both sides by 4, x equals 0. Now that I have both values, let's go ahead and write my ordered pair x and then y. So 0, 4 will be the ordered pair that functions as the solution to this linear system. In this third and final example of this video, we have this linear system, and it looks like the first equation is written x, y equals number, which is a good, but the second one is x and then equals number and y, so that's not so good. So let's go ahead and take this -3y that's on the right side and shuffle him over to the left side, and he'll be positive. So plus 3y then. And then we'll go ahead and rewrite that first equation right underneath it. Okay, so here we are set up, x, y equals our constants here. So we need to decide, are we going to eliminate the x's or are we going to eliminate the y's? So remember, in order to eliminate two of these variables, whenever I add these equations together, they need to cancel one another out. That means their coefficients need to be equal in number but opposite in sign. So one negative, one positive, and the same number. Well, here I have a 5x and a 3x, and there's not really an integer I can multiply by 5 to make 3 or 3 to make 5. So the x's aren't really a great candidate. But you'll notice for the y's, neither. So I can't multiply any integer by 3 to get 2 or 2 to get 3. But my y's already do have opposite signs, so that's nice. So since I'm not able just to multiply one of the equations by a number, we're going to have to scale both equations. So here's what that's going to look like. So this 2 with the y, I'm going to put up here. And this 3 with the y, we're going to put down here. And I'm going to go ahead and distribute through by 2 and distribute through by 3, because you'll see the y's will cancel nicely if 2 times 3 makes positive 6 and 3 times negative 2 makes negative 6. Well, okay, let's go ahead and scale both of these equations by a factor of 2 and factor of 3. So I have 10x plus 6y equals 16. And then with the second one, 9x minus 6y equals negative 54. So right away I see that my y's do cancel when I add these two equations. So 10x and 9x makes 19x, and 16 minus 54 should be negative 38. A quick division by 19 will give me x equals negative 2. Well, fantastic. Once I have one of the values, I can go ahead and plug it back in and get the other value. So let's go ahead and plug it back into the first equation maybe. So 3x, and my x value is negative 2, minus 2y equals negative 18. So negative 6 minus 2y equals negative 18. And just add 6 to both sides. So negative 2y equals negative 12. Division by negative 2 will give me y equals 6. So now that I have my x-coordinate and my y-coordinate, I can go ahead and write my ordered pair as negative 2, 6. And once again, I would challenge you, go ahead and plug these values back into both equations and just make sure I have true statements. But negative 2, 6 will be the solution for this linear system. And we did it by elimination.